Now, in this video, we're going to be looking at how statistics deals with uncertainty. Now, just to refresh our memories, let me go back to slide 4 that we covered in the previous lecture, in the previous video. And we said that in talking about the field of statistics, which again is the area of application, or it's the context in which we're going to be studying probability. So we said that in order to make decisions in the face of uncertainty, that uncertainty must be taken into account in the decision-making process. Now, we also realize the reality that when drawing a conclusion based on incomplete information, we can never be completely certain that our conclusion is correct. All right? And so with that in mind, the idea that we need to be able to somehow account for the uncertainty or incorporate that uncertainty into our decision-making process, we need to think about how statistics deals with uncertainty. How do we quantify that? And so how statistics deals with uncertainty. So again, uncertainty must be taken into consideration when making data-based decisions. Now, the way that we typically do this is randomness is intentionally injected into an experiment through either the sampling design in observational studies or through randomized treatment allocation in designed experiments. Now, let me just stop here for a second and just point out that in our department, the Department of Experimental Statistics, there are 2 courses that we have that deal with what we just talked about in this second bullet point. We have a course that is called Introduction to Sampling, or the Fundamentals of Sampling, depending upon if you're looking at the undergraduate course or the graduate course. But basically, they're both talking about sampling techniques, how to sample populations, how to obtain samples from populations in order to be able to make decisions based on that data, and how to sample those populations in ways that are efficient, all right, and in some cases most cost effective. And the other course that I'm referring to is a course called Design of Experiments, and that is at the graduate level only. And that is a course that talks about how to structure an experiment, and in particular various ways of applying or assigning treatments that are of interest and that we're studying in an experiment. The purpose of the experiment is to study the effects of these treatments on the experimental material. And so the Design of Experiments course, or Experimental Design course, looks at ways of assigning treatments to experimental units or the experimental material we're using in an experiment in order to get the most bang for the buck in terms of drawing conclusions. And so if you are if you're in a field of research where you are going to be making inferences about populations, sampling from populations, and I would highly recommend that you consider taking the sampling course. On the other hand, if you're in a field of study where you're going to be performing designed experiments and applying treatments to experimental units in order to study the effects of those treatments, then I would suggest that you consider taking the Design of Experiments class. But regardless of which approach we're talking about, or which context we're talking about, whether we're sampling from a population or performing a design experiment, in both cases, we are intentionally injecting randomness into the experiment. All right, and then when we go to analyze the data, we need to be able to take that randomness into account. So by intentionally injecting randomness into an experiment through either the sampling design or the design of the experiment, what this does is it creates a probabilistic structure that we can then account for in the decision-making process. And so that is the way that we account for or incorporate the uncertainty that exists into the statistical analysis. So in each of those contexts, whether we're talking about sampling a population or performing a designed experiment, it's very important that we understand how we injected that randomness, how we conducted that sample survey, how we sampled the population, or how we designed the experiment, and how we applied the treatments to the experimental units. So the particular sampling design in the case of an observational study, or the experimental design in the case of a designed experiment, determines the appropriate method of analysis and or the type of model to be used in analyzing the resulting data. And so that is why I'm saying it's extremely important. I mean, you have to know the design, the sampling design or the experimental design. It's extremely important to determine exactly how an experiment was conducted in order to identify the appropriate way to analyze the data. Because again, the way that you conduct your experiment, whether you're sampling a population or performing a designed experiment, the way that you conduct your experiment essentially dictates the way that you should analyze the data. All right, so now let's talk about the specific ways that we quantify uncertainty. And so uncertainty can be quantified in a variety of ways, using probability, but also using odds, or logits, or entropy. You've probably heard of the first two, probability and odds. You've probably heard of odds in the context of casinos or races or something like that, where people might be wagering. All right. You may not have heard of logits and entropy, but we're going to cover all these. We'll define each of these. Well, when I say we'll define them to the extent we can. As we'll see, some of these things can be defined in multiple ways. But we'll see that when we get there. Okay, so there are a variety of ways of quantifying uncertainty and chance, and statistics incorporates uncertainty into the decision-making process through the use of probabilistic models. Now, let's talk about each one of these approaches to quantifying uncertainty and chance individually. So the first we'll start with is probability. Now, I said that we were going to define each of these, and then I kind of chuckled, and we'll see why here in just a second. But so we're going to talk about what is probability, how is a probability obtained, how is a probability to be interpreted, and also what properties do probabilities possess. So there are several questions that we want to consider here beyond just what is the definition of a probability. Now, the reason I chuckled when I said I was going to define each of these terms, and in particular probability, is that there are actually three ways of thinking about probability, three ways of defining probability, or three ways of approaching the notion of probability. And these three ways are the classical approach, the relative frequency approach, and the subjective approach. Now, this is a typo here. I think I'm gonna fix this right now. Hold on just a second. Okay, so I've corrected that typo there. So the three ways of approaching the notion of probability: the classical approach, the relative frequency approach, and the subjective approach. Now, the approach that we use for in thinking about probability determines how probabilities should be interpreted. Now, let's first think about the classical approach. This is the approach that you're probably most familiar with in terms of a classroom type setting. If we think about probabilities involving tossing dice or flipping coins or pulling chips out of a bag or something like that, then you're typically thinking about the classical approach to probability. In fact, almost always you would be thinking about the classical approach. Courses in probability in, let's say, the high school level or even before that, they are probably, without exception, always going to be approaching probability from the classical approach. And so under this classical approach, the probability of an event is defined as the ratio, right, the ratio of the number of cases favorable to that event to the total number of cases. And so another way to say that is that the probability of an event calculated using the classical approach is going to be equal to the number of ways that that event can occur divided by the total number of possible outcomes. All right, so now this definition, now let's think about this. We're defining how we calculate it. We're doing it really a couple things. If you think about it, we're trying to define what we mean by the concept of a probability, but in doing this, we're actually defining how we calculate it. All right. So in this context, the notion of probability is really wrapped up very tightly with the way that we calculate it. Now, the thing is that this approach to probability is only applicable when the outcomes of the process that we're talking about are equally likely. All right? If we have a situation where the set of all possible outcomes are not equally likely, then the classical approach would not be an appropriate approach to use. Now, there are a lot of situations where the set of possible outcomes are not equally likely, and so the classical approach would not be appropriate. Now, with that definition and with that caveat there, in the second bullet point, what is the appropriate way to interpret such a probability? So I'm going to be posing questions here in this first section, and I'm not necessarily going to give you the answers. My purpose here is to pose some questions to get you to think about some of these things, hopefully in a little bit more detail and a little deeper than you have thought about them in the past. All right? And then these kinds of questions, and hopefully the answers will come up a little bit later in the course. So, with the classical approach to probability that applies only when the outcomes are equally likely, what is the appropriate way to interpret such a probability? What is its connection to reality? And then what does it mean from an operational standpoint? So think about those questions and try to interpret what they mean and try to come up with some answers to those questions regarding the classical approach to probability. Now, in terms of properties for classical probabilities, it can be shown that properties for classical probabilities can be mathematically derived. So there are properties that probabilities have, probabilities when approached from the classical approach, and those properties can be derived mathematically. Now, you might be thinking, well, of course they would be, the properties would exist, and of course that they would be derived mathematically, but I just want to point that out at this juncture. Okay, the second kind of probability is that we'll study is the relative frequency approach to probability. And in this, or using this approach, the probability of an event is defined as the limiting value of the relative frequency of the occurrence of the event in an infinite sequence of trials. So that is a much different way of thinking about probability than the classical approach. In the classical approach, we have what's really implicit in that definition, all right, and it's a necessary condition, is that the total number of possible outcomes is finite, all right, and that could be the case here as well. But in this situation, what we're thinking about is a sequence of trials, an infinite sequence of trials. And the probability of an event, so for example, maybe we're talking about flipping a coin, all right? There are two possible outcomes. A set of possible outcomes is certainly finite, right? So you can get heads or tails. And we might be interested in the probability of getting heads when we flip a coin. Well, according to the relative frequency approach to probability, that probability is defined to be the limiting value of the relative frequency of the occurrence of getting heads in an infinite sequence of trials. Now, that's, again, a much different way of thinking about probability than in the classical approach. Now, here are some questions that I might ask you, and I want you to be thinking about this. From an operational standpoint, can we actually construct or perform an infinite sequence of trials? For example, can we flip a coin an infinite number of times? Now, in a given situation, how do we know whether relative frequencies converge to limiting values? For example, if you said in answer to the second bullet point that from a practical standpoint, we can never perform an infinite sequence of trials, we can never flip a coin an infinite number of times, then if we wanted to talk about the probability of getting heads, how would we be able to tell whether the relative frequencies converge? Even if we, in fact, let me say this, even if we could perform an infinite sequence of trials, how could we know whether the relative frequencies converge to limiting values? Now, that may seem like a very easy question to answer. But the reality is maybe it's not quite so easy because, and we'll talk about this a little bit more later, but the outcomes of the trials that we're conducting, for example, flipping a fair coin, those outcomes are random. And because they're random, there is no mathematical function that we can use to predict what the outcome is going to be on a given trial. And because such a function does not exist, we do not have a function that we can take the limit of. All right? So having said that, let that kind of guide your thinking as you think about the answer to bullet point number 3. A corresponding question is, how can relative frequencies be determined? Okay, can we determine them mathematically? All right. I want you to think about that. Can relative frequency probabilities be determined exactly? So these are very interesting questions, and the answers may surprise you. Now, in order for relative frequency probability to be applicable or appropriate for a given situation, we must be able to frame the event of interest within an infinite sequence of identical trials or as part of a mass phenomenon. When this can be done, then clear-cut interpretations and connections to reality exist. So again, in order for this type of probability to be applicable, we need to be able to couch the event of interest, think about it in the context of an infinite sequence of trials, for example, flipping a coin or rolling a die, or as part of a mass phenomena. So for example, gas molecules in an enclosed box. All right, that would be an example of a mass phenomena. Or another example of a mass phenomena would be interactions going on in a population of people. The final point here that I want to make is that properties for relative frequency probabilities can be mathematically derived. So you'll remember when we were talking a few minutes ago about classical probability, we said that properties for classical probabilities can exist and can be derived and proven mathematically. And the same thing applies here, that properties for relative frequency probabilities exist and they can be derived and proven mathematically. Now, let me ask you a question. If you think about how much different the ideas of classical probability and relative frequency probability are, and how much different the definitions are, would you expect that the properties of those two types of probabilities would be the same? All right? And the second question I would ask is that, let's suppose that there is a property that holds not only for classical probabilities, but for relative frequency probabilities as well. would the proof or would the derivation for that property or of that property be the same under those two kinds of probabilities for the classical approach and the relative frequency approach, or would they be different? So be thinking about that. So classical probabilities, relative frequency probabilities, and then the last type of probability is the subjective approach to thinking about probability, or subjective probabilities. So under the subjective approach to probability, the probability of an event is a subjective assessment. All right, so it's a matter of opinion, so to speak. Now, because it's a personal assessment, the subjective probability of a given event can and probably will vary from one person to the next, or from one time point to another for the same person. So, for example, you could have, on a given day when you get up in the morning to get ready to come to campus, you may have some subjective assessment that it's going to rain that day, and so you take your umbrella. And then by noon, your subjective assessment of whether it's going to rain may change based on additional information about what's going on, in terms of the weather. All right, and even in a given situation, you might have two people, and we might be talking about the probability that LSU wins the next upcoming football game. All right, and two different people might have very different subjective assessments about the likelihood of that occurrence. All right, and so so the point is that subjective probabilities vary from one person to another, or can, and even within the same person, they can vary from one time point to the next. Now, one of the characteristics of subjective probability is that there's no prescribed way of determining the value of a subjective probability. There's no formula. Let's put it that way. When we defined classical probability, we gave, in the definition of classical probability itself, we gave the formula for calculating a probability. And when we defined relative frequency probability, when we defined it, we gave a way, at least conceptually, for coming up with that probability. But with subjective probability, we're really not defining it in such a way. It's not defined in a way that we can capture that calculation or that determination, that assessment, with a with a formula or some other mechanism. So there's no prescribed way of determining what a subjective probability is going to be for a given person, because it's that person's own personal assessment, and that can change over time. Now, a question that I would ask you is, what properties do subjective probabilities possess? All right, do they have the same properties that classical probabilities and relative frequency probabilities possess? Can they be derived mathematically? All right, so fairly interesting question to consider.